Well, good afternoon, everyone. Welcome to the Axsoft webinar on silica. What is it and why is it a problem? For those of you that don't know me, my name's Paul Rubens. I'm Managing Director at Axsoft. We're specialists in noise, vibration and air quality monitoring, instrumentation and solutions. We've worked with Sensidyne, who are a US manufacturer of dust monitoring equipment, for over 10 years now. They're probably best known for their brand Gillian, which has been around in this particular market for 60 or 70 years now. This afternoon we have a guest speaker from America, Aaron Apostolico. We've known each other for many years. Aaron is a corporate industrial hygienist, so he's actually a certified IH and does the in-house industrial hygiene work for the Sensidyne group. So we're pleased to welcome him to speak to us this afternoon. So without further ado, Aaron, over to you.
Thank you very much for the introduction, Paul. As Paul mentioned, we are going to talk a little bit about silica, exposure, why it's a problem, and we're going to get into a little bit about some health effects and really what to do about it and how to prevent it. So I just want to go over the outline of my presentation. Make sure. Here we go. So as an outline, we're going to really cover what is silica, why is silica a problem, some general rules globally around silica, and then I'm going to talk about some UK specific rules. As I mentioned, some international regulations, some World Health statistics, some key industries and specific operational tasks that have airborne respirable silica produced. We'll go over a couple case studies. We're going to talk about some sampling strategies, some very specific equipment and accessories. I'm going to talk a little bit about the silica analytical methods from the laboratory side of things, and then we'll end with some general conclusions. So again, welcome to everyone that's joining us today. Let's start by really understanding what is crystalline silica. It's a material that is really present ubiquitously throughout the world. The elemental compound is silicon dioxide. It makes up 15% of the Earth's crust, and it's in very common materials such as sand, granite, and other hard rocks. Now, crystalline silica really is broken up into three forms, which most of people are familiar with quartz as the most common form, which is in your typical concrete mixtures. And then less common forms such as cristabalite and tridymite are still present in several substances, but are much less common. Now, all crystalline silica forms have diagnostic X-ray diffraction patterns, and this is really what allows us to speciate one species of crystalline silica from others. So when we talk about, the compound silicon dioxide, let's break it down. So silicon is the second most abundant element on Earth. Silica, as we refer to it, is really a combination of that silicon element and oxygen, not to be confused with silicates, which is a combination of silicon, oxygen, and metals. And definitely not to be confused with silicone, which is that synthetic polymer with properties similar to rubber. So we hear the term crystalline silica, and this is one form that is really a crystalline solid where the molecules are really tightly and uniformly arranged, as opposed to amorphous silica, which is a solid where the molecules are more randomly arranged. So when we refer to the types of silica dust in air, we have this amorphous silica and we have the crystalline silica types. And for those that aren't really clear of what these different types look like, I have some images here to illustrate that. So on the left, we have an amorphous silica. This is a metallic glass. Things like volcanic rock are also amorphous in nature. Here you see cristabolite. Now, this is a piece of volcanic rock, but within it, you see these white snowflake spots. That is the cristabolite silica. In the center there, we have quartz, and then on the right, we have the tridymite. So I mentioned earlier that quartz is the most common form of crystalline silica, with cristabolite and tridymite being less common. But even within the realm of crystalline silica, we want to really think about it in terms of hazards. So hazards really are discernible by their particle size. So particles that are larger than 10 microns, usually up to 100 microns in size, are really an inhalable fraction. Not that this presents no danger, but most certainly less than those smaller particles, let's just say less than 10 microns, that can get into the thoracic region of your lungs. And then we have the respirable fraction. And these are the very small particles, less than 4 microns in size. And I'm going to talk to you a little bit further about why these smaller respirable fractions of crystalline silica are so harmful. So again, to reiterate, not that there's zero harm associated with larger particles or these other forms, but it's definitely a lesser hazard than thoracic fractions, and most certainly the most hazardous form is going to be the very small respirable fractions, less than 4 microns in size. So let's talk a little bit about why silica is as big of a problem as it is. Millions of workers are exposed to occupational hazards involving silica on a regular basis. Amongst those workers, probably the most at risk are going to be within the construction industry, heavy equipment operators, and plasterers or drywall workers, because the binding agents in most of those materials are crystalline silica, as well as the ability for them to become aerosolized by the tasks that are performed. On a global scale, at least 227 million workers are employed in high-risk industries worldwide that involve respirable crystalline silica, with known over 1 million children working in these industries worldwide. Exposed people are often the most vulnerable and disadvantaged, as well as medically underserved, which leads to the most medical conditions and, unfortunately, large health hazards and fatalities. Respirable crystalline silica particles has been classified as an occupational airborne particulate of worldwide concern as a result of this large worldwide exposure. Over 20,000 new incident cases of silicosis were identified in 2017 alone. Hundreds of millions continue to be exposed to respirable crystalline silica in the workplace, and the true number of incidents is probably much higher due to deficiencies in reporting on occupational respiratory health surveillance in many countries. Now, recent outbreaks of silicosis has been associated with the fabrication of kitchen bench tops, and this is notable because of the young age of affected workers, the short duration of their respirable crystalline silica exposure, and the rapid disease progression. So what we've seen, and why this has really become as large of an issue as it has, is that workers that are really grinding and cutting these kitchen countertops, these granite kitchen countertops, as well as some other materials that contain the crystalline silica form, very high aerosolization. Most often they're not properly protected, and we're seeing workers again, very young age, less than 30, having only worked in the field for several years, start developing symptoms of disease. Now, despite countries around the world dealing with these similar issues related to crystalline silica exposure, the global public health response is both low, and there's really a lack of consensus about occupational exposure limits that would provide protection to workers. And I'm going to talk a little bit more in some upcoming slides about different exposure limits worldwide to really illustrate the lack of consensus. It's important to note also that many low and middle income countries either don't have any legislation or an occupational exposure limit to really govern that exposure. So talking a little bit about some world statistics, in 2017, regional incidents of silicosis were as follows in Asia. In East Asia, over almost 16,000 cases of silicosis. Southeast Asia, 656 cases. Central Asia, a little less at 18, and South Asia at over 2,800 instances of silicosis. Now, the region of East Asia had the highest overall age standardized incident rates of 0.78 per 100,000, and that's really high when you talk about occupational illnesses. At a national level, the highest increase in average in annual percentage change in the ASIR was noted to be in Singapore, and globally, the highest number of incident cases were in China with over 9,000 cases, followed by India with over 1,400 cases. Again, from an international example, India, where there's an estimated 10 million workers are exposed to silica dust annually. Now, most of these exposures occur in construction and mining industries, as well as in rock quarrying industries. The prevalence of silicosis can range widely, anywhere from 3.5% all the way up to 54.6% in high-risk working groups. Now, that's a really high prevalence of disease associated with an occupational exposure. And from an industrial hygiene standpoint, having that level of incidence on any type of occupational illness would usually garner a higher response than we're currently seeing. Another international example is in South Africa. The South African mining industry, particularly in the gold, coal, and platinum mining occupations, have been identified as high-risk sectors for silicosis due to extensive dust exposure during these mining activities. The disease often remains asymptomatic for years, making early detection and intervention challenging. So we're going to talk a little bit about symptoms of disease. We're going to talk a little bit about the latency period associated with it and why there's such a slow response a lot of times to react to these long-term health effects. So in the UK, for the period between 1996 and 2017, there were, I believe, a little over 216 cases of silicosis reported. The mean range of ages for those was 61 years, with a age span from 23 all the way to 89. So it really shows that, it can be exhibited in really any age of worker. With the majority, 98% of these exposures cases being male, and across all industries, 65% of those cases were diagnosed in individuals of working age, which is less than 65 for men and less than 60 for women. Again, another UK statistic, an estimated 600,000 workers are exposed to silica each year in the UK. I believe I lost my webcam. Let me go back to it real quick. I apologize. Sorry, a 2019 occupational environmental medicine study for the UK for silica This was co-authored by researchers from HSE's Center for Workplace Health, concluded that silicosis remains an important health problem in the UK, affecting workers of all ages across a very wide range of industries traditionally associated with silica exposure. They also added that the majority of these workers reported to have silicosis were still of that working age. And the authors also noted that silicosis was reported in young workers across these industry groups, with around 1 in 6 of these workers being under the age of 46, which again is very problematic for occupational diseases that can take 15, 20 years in some cases to really start showing those more severe health impacts. So let's talk about how silica really affects us. Exposures to respirable crystalline silica has been linked to really the following occupational diseases. So that's silicosis, lung cancer, chronic obstructive pulmonary disease, also known as COPD, kidney diseases, several autoimmune diseases, as well as tuberculosis and a newer coined terminology, silicotuberculosis. Now, disease may occur in a matter of years, or it could be decades later. I mentioned in an earlier slide about the different particle sizes and how they have different hazards, associated with them. So here we have a slide of the human respiratory tract, and again, you can see the inhalable dust fraction. This is, those particles that are less than 100 microns in size. A lot of these get filtered out. I apologize. It keeps advancing on its own. Let me see if I can stop that. Okay. A lot of the larger particles will get filtered out by the upper respiratory tract. We have the thoracic region, which is that upper respiratory fraction, and then we have the respiratory fraction, which really gets into that lower bronchial region of the lungs. Now, there's 3 types of silicosis. There is chronic, there is accelerated, and then there's acute. Now, chronic problems may not show up until decades after you're exposed to low or moderate amounts of silica. It's the most common type of silicosis, and symptoms may be mild at first and then slowly and gradually get worse. You have accelerated, which now you'll notice signs about 5 to 10 years after heavy exposure to silica, but then symptoms can actually worsen quickly. And then you have acute, like we were talking about with the cutting of kitchen countertops and that industry with granite kitchen countertops, where symptoms happen a few weeks up to 2 years after exposure. And this is really to a large amount of silica. It's kind of scary. You see these 2 images in this slide of both a healthy lung and a lung with silicosis. And you can really see as the disease progresses how much damage and scarring it causes to the lungs. It's important to understand that these health effects are both permanent and irreversible. They can be debilitating at first, but it can also lead to lung cancer, and unfortunately, many deaths are associated with high progression of this disease. So how does the health effect occur? So when you breathe in the respirable silica and it gets into your lower lungs, it causes these microscopic lacerations of the alveoli. When this occurs, it actually forms scar tissue, and this can create fibroids. Many times it's non-detectable because it's less than 1 centimeter in size. As it starts growing and scarring gets worse, it can now be observable by x-rays. The scar tissue and fibroids can prevent the exchange of gases in the lung tissue. So this is really that oxygen and CO2 exchange. This leads to basically your body becoming starved for oxygen. Once this actually occurs, the condition is irreversible. There is some treatment with bronchodilators that may provide some temporary relief of the disease. early on, but as it progresses to the more advanced stages, they will have minimal effects. Often medical oxygen becomes necessary as the disease progresses because the body just cannot get enough oxygen into your system. Patients typically have a cough and shortness of breath. They exhibit weakness and tiredness, and it can lead to death. Early diagnosis can be through both, a good work history, as well as chest x-rays, as well as pulmonary function tests and spirometry. Many times, silicosis itself is misdiagnosed as tuberculosis, and as I'll talk about in an upcoming slide, a lot of times it's a combination of tuberculosis and silicosis because of the susceptibility that occurs when workers are exposed to silica and early stages of silicosis is occurring in the body. They become more susceptible to tuberculosis as well. Again, tuberculosis is a highly contagious disease. Silicosis increases the risk of TB by up to 4 times. Patients have a cough, sometimes with blood, chest pain, shortness of breath, tiredness, and unfortunately, there's many occupational deaths that are misdiagnosed as related to tuberculosis as opposed to silicotuberculosis, which really was the onset of that disease. The International Agency for Research on Cancer, the IARC, classifies silica as a known human carcinogen. Again, they dictate that patients can have cough, shortness of breath, chest pain, coughing up blood, tiredness, weight loss, and it may lead to death. Again, diagnosed by symptoms and imaging, both with a chest x-ray or a chest CT scan. I mentioned COPD. Air is obstructed from getting out of the lungs and leaving less room to bring in oxygen. Patients may have chronic cough, phlegm, again, shortness of breath and wheezing. This often leads to exacerbations and infections within the lungs, and it causes long-term disability. And again, as it progresses, it can also lead to death. This, again, is typically diagnosed through medical history workups. Pulmonary function tests definitely are preferred if available. And then, of course, and it should be of no surprise that cigarette smoking adds to the lung damage caused by silica and contributes significantly to the development of lung disease. Now, not all diseases associated with silica are lung diseases. There is evidence that exposures can increase the risk of kidney disease. There is some evidence that exposure increases the risk of scleroderma. Patients may have a thickened skin, stiff joints, tiredness, and poor blood flow, also as a result of higher exposures to respirable crystalline silica. So what are some signs and symptoms to really look out for? Early on, there might be no symptoms at all. As it progresses, coughing and shortness of breath, I would say considerable coughing of a phlegm, of sputum, fever, weight loss and exhaustion, chest pains, swollen legs, and then of course, as it advances and you're not able to get enough oxygen in, you might see symptoms such as blue lips. So how do you know which employees are being exposed? So we're going to kind of switch gears here and move from really the hazards of it to, okay, here's the risk assessment. It really should include a hazard assessment, identifying any and all items that may cause harm to those employees. And you would identify this through personal monitoring, area monitoring, and review of objective data. The risk assessment, determining the severity and likelihood that exposure to a hazard will cause injury or illness. So things like frequency of exposure, duration of exposure, and then the concentration that's present compared to the OELs. What actions can prevent and mitigate exposures to the hazard? Well, of course, you need to develop a program to protect the employees in the workforce. You need to utilize the hierarchy of controls, and we'll talk about those a little bit more. And then you really need to strive for continuous improvement in the workplace to continue to implement a program that's really going to protect the health and well-being of your employees and the workforce. So occupational exposure limits. These are really used to both assess and communicate the risks that are in the workplace. An OEL is an acceptable upper limit of exposure. Sampling requires testing with air sampling pumps and analyzing samples at a laboratory. The laboratories offer the proper analysis, and in order to really find respirable silicon particle size, you must use a size selective device. These are typically cyclones or particle impactors. I'll talk about those a little bit more. But respirable fraction, again, is that less than 4 microns in size, and again, compared to the respirable occupational exposure limit. As a general rule of thumb, if you see high levels of dust, there's likely respirable dust in that, and there's probably a problem that's present in the workplace. So I want to talk a little bit about the history of exposure limits. Most certainly they've changed over the years. I'm going to speak largely to our OSHA limits here in the US, and then I'll kind of circle back to some of the UK limits and where they stand. But previously, permissible exposure limits for silica were calculated using formulas, and these were very complicated. They were hard to understand. It was a percentage of the overall dust. There were separate limits for construction and shipyards that were looking at certain particle counts. For general industry, the formula for the permissible exposure limit ended up working out to be equal to around 100 micrograms or 0.1 milligram per cubic meter. For the construction and shipyard industries, the formulas worked out to be around 250 micrograms per cubic meter. And then, you know, I would say on a global consensus, but most certainly in the US as well, there came to being an understanding that the previous exposure limits were not adequately protecting workers. We were still having high incidence of silicosis as well as fatalities with exposures that were, you know, significantly lower than what the occupational exposure limit was. So, you know, this came from extensive epidemiological evidence that both lung cancer and silicosis can occur at levels below 100 micrograms per cubic meter. So let's talk about various silica rules and occupational exposure limits. So, you know, today, the UK, the HSE has a permissible exposure limit of that 100 micrograms per cubic meter or 0.1 milligrams per cubic meter. The US recently, a few years ago, reduced it to about half of that. So our new limit is at 0.05 milligrams per cubic meter with an action limit established of half of that limit at 0.025 milligrams per cubic meter. And I'll talk a little bit more about what the action limit is and how that's utilized to, I would say, implement certain actionable items when limits are above or when exposure is above that limit. Canada has a permissible exposure limit of 25 micrograms per cubic meter. Colombia, Costa Rica, Mexico, they follow the ACGIH limit, and the ACGIH TLV TWA for silica for quartz and cristabalite is set at that 0.25 milligrams per cubic meter. Brazil still calculates silica percentage first, but also uses that ACGIH TLV as a best practice. Argentina has separate standards for silica quartz. Again, it starts with that ACGIH TLV for the silica quartz at 25 micrograms per cubic meter. And then for cristabolite, it's at 50 micrograms per cubic meter. Peru has a limit of 0.05 milligrams per cubic meter. And then South Africa also has a range ranging from the 0.05 all the way up to 0.1 milligrams per cubic meter. So again, over on my side of the pond, we deal with OSHA. Now, OSHA standards have been adopted, again, in many countries around the world. They have similar standards, but we set our permissible exposure limit at 50 micrograms for an 8-hour TWA with this action limit of 25 micrograms. We do recognize the ACGIH TLV of 25 micrograms as an 8-hour TWA as a best practice. Within our rules and standards, an exposure, assessment is required if exposures are or may reasonably be expected to be above that action limit of 25. Exposure assessments can be done using a performance option or a scheduled monitoring option. I can tell you most often we use a scheduled monitoring option where we go out and we collect data sets periodically throughout the year to demonstrate that we're in compliance, or if we're above compliance, that we're taking necessary actions to prevent those overexposures in other forms and fashions to the employees. So as I mentioned, in the US, our PEL is at 50 micrograms per cubic meter. That is based on an 8-hour time-weighted average. Our action level is set at 25 based on an 8-hour time-weighted average. And then the most current recommended industry exposure limit is the ACGIH TLV, which is the 25 micrograms per cubic meter over an 8-hour time-weighted average. I really like this slide. I think it does a good job of putting in perspective how little silica dust is required to be at that occupational exposure limit. So what you see in this first picture is a US dime. All right, a US dime pretty much is about the width of your fingertip. Next to this, you see two little piles. Each one of those piles represents approximately 500 milligrams of silica. All right, that little amount. And then the picture on the right is showing an average room of 20 cubic meters of air. So if you had just one of those piles in that room aerosolized, all right, that would represent 500 micrograms in a 20 cubic meter of airspace, 25 micrograms per cubic meter. You would be above the TLV or that action limit. All right, two of those little piles puts you over 50 micrograms, all right, over the US PEL. And then of course, just four of those little tiny piles, all right, would be well over 100 micrograms per cubic meter, which is the current UK standard. So in the US, OSHA recognizes that levels above that 25 micrograms per cubic meter needs to trigger, certain actions such as medical exams. And I talked about early diagnosis through pulmonary function tests, through chest x-rays, chest CTs. So if you have employees and you have exposure hazard assessments that are above that TLV for more than 30 days in a year, these employees need to be part of a medical surveillance program. Companies are required to have a written exposure control plan. It must include it must include a person responsible for implementing the plan. all tasks that may involve exposure to silica, and then for each task, the specific method used to limit silica exposure, as well as general housekeeping measures to be used to limit exposure to silica. Sorry, I had an understanding that my pause version of your screen. Click here to resume. Just want to make sure everyone can still see my screen. So these are different factors associated with general housekeeping measures for controlling exposures to silica. There's regulated areas. So the employer shall post signs at all times and entrances to these regulated areas that bear the following. Danger, respirable crystalline silica may cause cancer, causes damage to lungs, wear respiratory protection in this area, and authorized personnel only. As you can imagine, it makes sense that we want to restrict access to those people who are not being protected. And we have to determine this through, air sampling and through delineation, what is the distance away, what is that zone of hazard, and at what point past a certain area is personnel safe. I mentioned briefly about medical surveillance. It must be offered within 30 days of initial assignment to tasks where silica exposure is prevalent. And then it should be performed at least every 3 years, but in general, most employers have a 3-year medical surveillance period. Medical exams for silica must include a medical and work history evaluation, a physical exam, an x-ray, a tuberculosis test, because we talk about those that have exposure to silica as well as tuberculosis have a much higher likelihood of progression of the disease as well as death. And then a lung function test. This uses an instrument called a spirometer. It's used to really measure how much air you can blow out and how fast you can blow it out after taking a deep breath. So, of course, if you have progressions of lung disease, you have diminished lung capacity, and this is definitely a quick, easy way to determine if you have progression and decreased lung capacity from previous years. Communication to the employee must be provided. So within 30 days of the exam, there must be an explanation of the medical conditions to the employee. There must be recommendations and limitations on respirator use and exposure to silica. And again, this only goes to the employees because it is a protected data set. The written medical opinion must be provided. A copy of that opinion goes to the employee, and then proof of the exam for future employers must also be made available. Here in the US, as well as many places around the world, employers must cover costs of the exam, the tests, as well as the time spent traveling and getting the exams. Employers must have other health and safety programs and training to support the respirable silica program that they have for their facility. These would include hazard communication, so a review of the materials being used and associated hazards. A lot of times you'll find this on the SDS. You'll know if that material contains crystalline silica, and then by just the process and task itself, whether or not the hazard can become airborne and there really is an exposure concern. Companies must also have a respiratory protection program. Typically, it is used as one of the controls as part of the hierarchy of controls. We'll talk about that a little bit further in an upcoming slide. A copy of the standard. Employers must make the regulatory standards available to employees upon request. It's important to note that different countries have specific standards. Some employers have employees that travel and work in different countries. They must know those standards and comply with them. Different states and regions and even local municipalities may have their own standards that govern exposures to respirable silica. Employers must keep medical and exposure records, typically for the duration of the employee's work lifetime, based on regulatory requirements. And of course, they must make them available to the employees upon request. So some alternate exposure control methods for exposure assessments. This is where regulators require that employers do the following: identify potential exposures, perform representative air sampling, let representatives observe the air sampling. They must provide the results of the air sampling to the employees, and then of course, based on the findings, create these exposure control plans. So what do these written exposure control plans look like? Well, health surveillance for silicosis must be considered for workers in these high-risk occupations. This includes industries like construction, foundry work, brick and tile work, different quarry work and stone work, where workers are regularly exposed to respirable crystalline silica, and there is reasonable belief that silicosis may develop. Health surveillance must be provided. And further examples of where health surveillance for silicosis may be appropriate would be where there have been previous cases of work-related illness, where there is a reliance on respiratory protection for controlling exposures to respirable crystalline silica, and then of course where there's evidence of work-related ill health within similar industries. So I wanted to go into a little bit more depth of specific industries where these exposures to silica commonly occur. As I mentioned, mining and quarry work, construction, pottery and ceramic work, glass manufacturing. It's commonly found in structural clay products, concrete products, foundries. And then there's other, instances that might not be as well understood, like dental laboratories, certain paintings and coatings operations, jewelry production, and refractory products, asphalt products, agriculture and landscape. If you think about, 15% of the Earth's crust is made of silica, and all the tilling and all the heavy equipment that is running in the agriculture and landscaping industries is commonly aerosolizing this material, which again makes it more hazardous to those farm workers. Tunneling operations, stone cutting operations, particularly I talked about those kitchen countertops. And then there's many abrasive blasting within multiple industries. So maritime work, abrasive blasting in construction, as well as general industry. Furnace installation, again, setting railroads and doing rail work, shipyards, and then we've also seen instances of exposures associated with hydraulic fracturing for both gas and oil. So some specific tasks within manufacturing, abrasive blasting, glass making, making soaps and detergents often has tasks involving exposures to silica. Again, anything that disturbs the soil within the agricultural industry. Within ceramics, again, just manufacturing, clay and pottery work. Within the construction fields, sandblasting, rock drilling, masonry work, jackhammering, tunneling, foundry work, grinding, molding, shaking, core room work. Again, high potential for aerosolization. Within mining, the cutting and drilling through the rock, railroads, setting and laying track, shipbuilding, abrasive blasting operations are usually a task with high exposure, and then stone cutting, sawing, blasting, chipping, and grinding of stone usually results in higher exposures. So now we're going to get into measuring exposure to silica. So why measure the concentration? Of course, we need to know how much is present if we want to be able to both prevent disease and protect people from silica. We have to know where it is and we have to know how much is there. Hold on real quick. So collecting samples. Yeah, I mentioned that we need to collect. We collect samples in a worker's breathing zone. Typically, we're using a form of a cyclone, and dust particles from the air are pulled into this device using an air sampling pump. It's pulled onto a filter, and then that filter gets sent off to a laboratory for both gravimetric weight as well as speciation. The smaller sized respirable particles must be separated from the larger particles when measuring exposures using a size selective device. And it's important to understand that there's various cyclones out there, as well as personal impactors that may be utilized, and they might be used for different applications. And again, they come with different sizes, and there's quite some variability between them. So proper sampling for silica. The sampling pump should be worn for the entire duration of the work shift to get that 8-hour time-weighted average. This way, the results can be compared to those OELs, and the OELs are often a basis for assessing the risk, making recommendations, and instituting the necessary controls. That being said, there is value in understanding what a specific task may present. So short-term or task sampling may also be helpful. This can ensure the minimum, to ensure the minimum volume is collected. I'll talk a little bit about why that's important when we talk about the actual methodologies and laboratory analysis. We need to collect higher flow rates. So a lot of times, if we don't collect enough volume, you'll be below the laboratory's limit of detection or limit of quantification. And in order to get around that, there are cyclones that can be used with higher flow pumps to basically collect at a higher flow rate to get that higher volume in order to meet that laboratory's limit of detection. So in addition to some task samples or these short-term samples, area sampling may also be useful. There is equipment out there that can determine some real-time monitoring for particulates. There's also fixed systems that can be installed that can do some continuous monitoring for real-time particulates. Technology is advancing, but there's still no real exact way to speciate in some of the real-time monitor equipment like there is using the advanced laboratory equipment. So back to air sampling for silica, the flow rate of the sampling pump must be carefully calibrated. Why? Because you're using a size selective sampler that basically operates off the principles of particle flow dynamics. This can be very complicated, but in truth, it's airspeed and particle diameter that's basically going to spin around in the cyclone. And then heavier particles of larger sizes will end up dropping out, and those lighter particles, which is that respirable fraction, will then get pulled up onto the filter media, which then gets sent off for analysis. The filters are typically analyzed using two main methods. That's X-ray diffraction, also known as XRD, as well as infrared IR analysis. The filter is also weighed before and after sampling to determine the total weight of that respirable dust. So here, I have an illustration of air sampling according to the OSHA standards. And here you can see that there are several methodologies that are used. We have an OSHA ID. We have 3 different NIOSH methods as well as an MSHA method. The NIOSH is used in general industry, whereas and OSHA is used for general industry, whereas MSHA is more specific to our mining industry. That being said, The analysis type is really limited to those two methodologies, being both XRD and IR. When the new occupational exposure limits were released, and it went from that 100 micrograms per cubic meter down to the 25 micrograms per cubic meter, we needed really a level of detection that went, well below it in order to really make sure that the representative sample was really above or below that actionable level. Previously, using the formula that you see with a very commonly used cyclone, a Dora-Oliver cyclone, this is that nylon cyclone that operates at 1.7 liters per minute. Basically, we said that you can sample for 8 hours, and if it's a very low exposure environment, you would be below the laboratory's limit of detection. So how do we get around that? We basically have several different alternative cyclones that are on the market that sample at a higher flow rate. I'll give an example, the GK 2.69. It uses a standard 37 millimeter filter cassette. It samples at 4.2 liters per minute. And sampling at that for your 8-hour TWA really helps to ensure that you have a significant amount collected that meets the laboratory's limit of detection and limit of quantification. So some best practices to consider is drawing a large enough sample to obtain that limit of detection, using the analysis through XRD or IR as described in those 6 methods. Observe the cyclone flow rate specification for meeting the appropriate size selection curve. So this is dictated by the manufacturer of the specific cyclone that you're using. So as the example I gave of 4.2 liters per minute, you want to be as close as possible to that exact flow rate to really make sure that you are capturing right at that 50% cut point for the 4 micron particle diameter size. It's important that you use a constant flow control pump that will keep the flow rate within plus or minus 5% of that set flow. A constant flow pump, again, will adjust its flow rate as back pressure, this is the loading of the filter cassette, occurs. It's important that that flow rate adjusts appropriately to make sure that you're maintaining that size selection curve. And a medium flow cyclone can meet the detecting limit in an 8-hour sample and still be comfortable to wear. Again, sampling at that higher flow rate, such as that 4.2 liters per minute, again, can be non-intrusive to the employee, but also make sure you're collecting enough volume to be within an acceptable limit for the laboratory analysis. So here are some things to consider when choosing a cyclone. There's cyclones with various flow rates and media sizes. Most commonly, we're using 37 millimeter filter cassettes. Typically for this type of analysis, we want to have pre-weighed or matched weight filter cassettes. But things we want to consider are, how visibly dusty is the process or the environment that we're collecting in. If it's a very heavy, dusty environment, collecting with a sampler at a lower flow rate is probably going to be fine. If you're in a very light dust environment, but still want to see if you're meeting the 25 microgram threshold, you would probably want to sample using a higher flow rate cyclone. You need to consider how long you want to sample for. If you want to take a task sample, or if you're collecting an 8-hour sample. You want to consider the diameter and pore size of the filter. Why? Because this can impact the back pressure as seen by the air sampling pump. You know that all air sampling pumps have limitations and fault points associated with them, and that if you exceed the back pressure level, because you're using a smaller filter head, as well as a smaller diameter pore size, that you may fault out the pump and not get your full shift sample. Is your media pre-weighed? Most commonly, again, for this type of sampling, we choose to use pre-loaded and pre-weighed filter cassettes. It's important to know the manufacturer's flow rate specific to the cyclone that you're using. And then some cyclones can independently measure both thoracic as well as respirable fractions. When they do that, they would use different flow rates to capture both that thoracic, which remember I mentioned earlier is that less than 10 micron particle diameter size, versus the respirable fraction, which is the less than 4 micron particle fraction size. I mentioned it earlier, but this is an illustration of really how a cyclone works. Air gets pulled in, and then it really spins around the outer edge of the cyclone. Those heavier particles will actually fall and drop out into a reservoir known as a grit pot. The lighter particles will actually get pulled back up, through a orifice into the filter media, and then adhere to the filter itself. It's important that you understand that that grit pot, again, should remain in its vertical orientation as much as possible. We have seen instances where people will turn their cyclone upside down, and then, of course, the material that was put into the grit pot can get put back onto that filter media, causing a bias to the sampling event. I mentioned earlier that there's other ways to do some direct reading. There's dust meters and nephelometers. Nephelometers, a fancy term for looking at these clouds of dust that are in the air. While not necessarily speciating what the dust is made of, these can be a good indicator of are my controls working? It could be a good indicator for delineating a roped off area or a taped off area where respiratory protection might need to be utilized, or where only authorized personnel can work. Again, these operate typically off a light scattering technology. The air is drawn in through a chamber. The light scatter basically looks for reflection and calculates a concentration based on that. Again, these can be useful accessories, but they do not distinguish silica from other particulates that are present in the air. I mentioned earlier you want to take a representative sample, but you can also consider objective data. So if you have knowledge about work activities and you're using the same equipment and the same materials being worked on, but maybe at a different location, that can be considered objective data, and you can utilize that for the purposes of determining an exposure level and making sure that you have the right protections and program in place. You're referring to some common issues and customer experiences. I mentioned back pressure and faults. You can see in this illustration that to maintain a constant flow rate, as the back pressure increases, the pump's motor has to work that much harder. This does two things. One, it drains the battery quicker, and two, it can stress the motor to the point that it's going to fault out. So it's important to really keep an eye and have a general understanding of the work environment to make sure that you're using both the right pump, you're using the right filter, as well as the right cyclone and flow rate that will work best in the environment that you're performing these samples in. Again, calibration of the air sampling pump is also key. You want to use a proper calibrator. We highly recommend, and it's a best practice, to use a 1% calibration device, especially with calibrating cyclones, because you want to be as close to that center line for the particle size curve as possible. So using a good quality 1% calibrator will help you achieve that flow rate on your sampling pump. Note that some cyclones do not have an inlet attachment point, so you might need an accessory such as a calibration jar, or sometimes there's other accessories that might go over the inlet point that is not readily attachable by tubing. So if you do purchase a cyclone that does not have that, make sure that you understand what accessories might be required for use with that particular cyclone. Again, calibration reliability, for that size selective devices like cyclones, using that specific cut size, you want to make sure that the calibrator itself is not causing an artifact. I know that there are calibrators out there on the market, typically associated with piston and piston styles, that might cause pulsation within the air sampling pump itself. So if you can imagine that you have a constant flow pump and that pump is reacting to, let's just say, a pressure change that is caused by the calibrator, then this is a bias that could affect that accuracy of your flow rate. So just be aware of that in choosing the right calibrator for use with a size selective device like a cyclone or particle impactor. The reason why is you can be accurate but not precise. You can be precise but not accurate. Ideally, you want to be both precise and accurate when calibrating your air sampling pump, which really ensures that you're at the desired flow rate and that there's not an artificial bias associated with that calibration event. Again, I wanted to differentiate the difference between both gravimetric and silica concentration. Gravimetric is going to weigh the weight of the filter, but there can be other materials, both organic and inorganic, biological, that can be present in order to get the concentration of respirable crystalla with speciation, usually quartz, cristabolite, and tridymite. They must use that IR or XRD analysis in order to get that speciation. I'm not going to go into a lot of depth about the different analysis, but what is important to note is that there are specific fingerprints and wavelengths associated with the X-ray analysis and the IR analysis. When they do use these techniques, they're able to identify the specific fingerprint, and you see at the bottom of this side, the absorption band, really helps to identify its structure, so we know that it is a peak associated with quartz as opposed to a peak associated with cristabolite. One of the big distinctions or differentiations between the XRD and the IR analysis is that the IR analysis can also differentiate between amorphous silica and respirable crystalline silica. I know we're right at that hour time. Some of you may have some concern about dropping off. If you can stay with me just for another couple minutes, I wanted to just briefly talk about preventing and mitigating exposures. Many of you who are health and safety professionals should be well aware of the hierarchy of controls, which really go through elimination, substitution, engineering controls. When it comes to engineering controls for silica exposures, utilizing things like wet methods, isolation of the process, isolation of the workers, administrative controls, and then, of course, PPE as a part of that. Again, PPE is very subjective to the wearer, and as a result, it is still deemed the least effective control because it still relies on proper use, proper fitting of the employee. Things like sandblasting, again, there are specific blasting hoods and equipment that can be used. When it comes to substituting materials, instead of using silica as a material, we can substitute that out for walnut shells, metal beads, and steel shot. In some cases, chemicals can be used to remove surface coatings as opposed to the abrasive blasting, but be aware that sometimes in substitution, you may be creating a new hazard while mitigating a different hazard. So again, be aware of the hazards of the chemicals being used if using chemical stripping to replace the abrasive blasting. In some cases, using high pressure water can also be used as a substitute material for sandblasting. Enclosing a process can come in several different ways. Again, there's glove box operations. Utilizing things like covers on conveyor belts can minimize the aerosolization of dust. Introducing ventilation systems. And then, we've designed specific cabs that are enclosed cabs for heavy operating equipment. This is where there was a lot of exposure within multiple industries that have been mitigated by the use of enclosed cabs. Plus, it makes it a lot more comfortable for the workers. So a lot of times they're very happy to have equipment that has enclosed cabs. Typically, if you see these high visual dust emissions, it's a good indication that a control is needed. Engineering controls, primarily through wet methods, are found to be both cost-effective and a good way to control exposures. That being said, there are some drawbacks to using wet methods. Frequently we'll see them with cutting with saws, utilizing water basins, drilling with water pumps through drilling stems, grinding and hammering on pre-wetted surfaces, as well as using fogging and steaming and dust suppression techniques. One of the things that you need to be aware of, though, is you're going to concentrate this dust into this reservoir of water. If that water ends up drying up through evaporation, you're left with these very fine particles of dust that can now be aerosolized. So it's important that you get that level of dust in that water back up, or prior to it becoming aerosolized, use a dry like HEPA vac to collect that material prior to it becoming aerosolized. The most common dry collection method, as I mentioned, is through vacuum collection using HEPA filtration. This can be more expensive because it does require electricity as well as certain equipment. Cutting with a vacuum system affixed to the saw blade. Again, many manufacturers will now have these accessories that you can use with their cutting equipment and drilling equipment, as well as grinding equipment with shrouds that surround the grinding wheel. We've seen that this really decreases the dust that becomes aerosolized, and there is a high reduction in exposures as a result. Some recommended policies when we talk about administrative controls: perform routine housekeeping, prohibit dry sweeping, because dry sweeping is just going to further aerosolize it. You can implement wet sweeping methods as an alternative. If services are available, make sure you institute a medical monitoring program. Consider keeping doors and windows closed for worksite machinery. And really educate and train employees on the hazards of working with respirable crystalline silica. We found that educated and knowledgeable workforce alone can really help mitigate the development and progression of this disease. So I talked about some administrative controls, either using vacuums or wet methods as opposed to dry sweeping. Education and training, is always a part of your written exposure control plans, making sure that people are familiar with the hazards, how to protect themselves from the hazards, know what engineering controls are available to them, how to use them, and be familiar with that PPE and how to properly wear it. Again, there's many different types of respirators out there. Know what type is appropriate for the work you're performing. Know what the protection factors are for the different types of respirators, and understand that in heavy environments, not only might the exposure to inhalation be an issue, but there might be concerns with ocular exposure. Getting dust in your eye can also cause workplace injury. So maybe utilizing a full face respirator as opposed to a quarter or half face respirator. Again, using the right filtering cartridges as well. Typically, you would use a P100 HEPA filtration device. If you do have a respiratory protection program, again, you need to make sure that it's appropriately documented, trained, that filters are regularly changed out, as well as making sure that the employees are medically fit and approved for use of those specified respirators. Again, there's lots of things that employers can do to keep those dust levels down. We talked about instituting, elimination, substitution, engineering controls, really making sure that the workers are following them, and then performing, periodic inspections of the workplace, as well as periodic monitoring, exposure monitoring, to make sure that the controls are effective. I will note this, that sometimes, we saw how much, the little piles of respirable silica dust that were next to that dime. Even if there's not a visible level of dust present, there still may be enough that is above that threshold limit. So truly the only way to know is through periodic exposure monitoring. So even though that visible dust might be significantly reduced, in order to verify and validate that, exposure monitoring typically needs to be performed. Again, employees should be responsive to those work practices that are instituted by the employer. They should do things like avoid using compressed air for cleaning surfaces that just aerosolizes the dust. Instead, use water sprays and wet methods. We talked about substitution, using respirators properly. Also, avoiding things like eating and drinking and smoking near crystalline silica dust activities, washing hands and face before eating, drinking, or smoking. These are just good hygienic practices in general. And then quitting smoking is probably going to be one of the best decisions if you know that you're regularly working, because the prevalence of both smoke inhalation as well as silica is going to exacerbate that potential for that occupational disease. So this concludes my presentation today. I know I went a little bit long, but I will turn this back over to our host at Axoft for some final words.
Well, that's great. Thanks, Aaron, for a very interesting talk. There's an awful lot of information to digest in there. I'm sorry for the couple of technical issues we had during that, but the potential issues of doing things across the pond. For those of you that didn't realize, Aaron's actually based in St. Petersburg in Florida, where I assume it's a lot sunnier than it is here. We don't have time for questions now, but Joe, our marketing manager, will be making sure that everybody has a copy of our email address, which is sales@axoft.co.uk. If you want to send any questions to that email, then we will guarantee that Aaron gets a copy of them, and we will pester him and make sure that he answers them in short time frame. So thank you everyone for your time this afternoon, and we wish you well. Thank you.
Thank you, everybody.